Okay, so let's continue with the graph of the functions. So we are graphing the function f of x equals to x minus 1. So I'm showing you the several steps before you graph the function. In the part 1 of this video, the first thing that we solve is the domain. So we determine the domain, and then we look for the intercepts, and finally we identified the asymptotes. These first three steps can be named as DIA: domain, intercept, and asymptote. So after performing that, so finding the domain, find the intercepts, and find the asymptotes, you now need to find where the function is increasing and decreasing. And this is basically about the derivative. If the derivative is positive, the function is increasing. If the derivative is negative, then the function is decreasing. Okay, so we just applied this idea to the given function, and we were able to find, so we will be able to find the intervals in which the function is increasing or decreasing. Let's start with the interval in which the function is increasing. Okay, so, or actually we can after performing some steps, we can identify the intervals simultaneously. Okay, so the first thing that we need to do is to get the derivative. So this is a quotient, so we use the quotient rule. So by quotient rule, we have x minus 1 times 1 minus x times 1, low, the high, minus high, the low, and then everything over 2 the low squared. So this is the L, the low squared. Then we simplify. This is x minus 1 minus x over x minus 1 squared. In simplest form, this is negative 1 over x minus 1 squared. So the derivative, or with the derivative, we can identify the critical point, okay, or the critical number. Okay, the critical number will happen at the value of x in which the derivative is equal to 0 or the derivative is undefined, does not exist. Okay, now if you look at the function or the first derivative function, there is no way that this will become 0, because the only way that a fraction can become 0 is that when the numerator is equal to 0. So this option is no longer considered. So the second option, where is the derivative undefined? It's easy for us to see that because this is a fraction, and the moment the denominator is 0, then the function will be undefined. So think of a number. If you place it here, the fraction will have a 0 denominator. So this x should be 1 for it to be undefined. So the critical number is x equals 1. Okay, so if you will make a number line, the transition will happen, the possible transition will happen at x equals 1. Then we just investigate what's happening before 1 and what is happening after 1. A quick way to do that, although there are many ways to identify the behavior of the derivative, so we have to inspect the derivative. One of the fastest ways is just pick a good number before 1 and pick a number after 1. So say if x is equal to 0, I'll pick 0, and then I place it on the derivative. So this is negative 1 over 0 minus 1. That is a negative number over a positive number, so this will be negative. And then the behavior of the graph at the right of 1, so pick a good number, say I'll pick 2. If I place it here, that will also be a negative number. So although the x equals 1 is a critical number, if you look at it, this is negative, so it means the graph is decreasing. And then after the value of x, which is equal to 1, the graph is also or still decreasing. So to answer the question, where is the function increasing or decreasing, we could say from negative infinity to 1, I have to cut it at 1 because it's undefined at 1. The graph is decreasing, but it's not only there, it's also from 1 to positive infinity. On this interval, the graph will be decreasing. What about the intervals in which the function is increasing? If you look at this, there is no interval that is a positive. So that means there is no interval that the graph will be increasing. Okay, so there's only a set of values in which a function is decreasing, but there's no interval in which the function is increasing. Okay, so this will be the answer to this part of the problem. Now, so we move on to the next task. So we have, again, just a recap: domain, intercepts, asymptotes. We look for the intervals in which a function is increasing and decreasing. This time, so let's check the next question. Okay, so after identifying where the function is increasing or decreasing, so we want to find the maximum or the minimum point of the function. This is actually a follow-up to the previous task. Now, if you recall, we had the critical number at 1, but we found out that the graph will always decrease before and after 1. So if this is decreasing and this side is also decreasing, so decreasing, and then there's no value, so maybe it's an asymptote, and then the other part of the graph is also decreasing, so that means there is no, so as you can see, there is no maximum and there is also no minimum point. So this is just one of the cases, okay? So don't think there will always be no maximum or minimum points. Since there is no change from increasing to decreasing or decreasing to increasing, then there is no maximum or minimum points. So the answer to this task is that there are no, or just say none, okay? There are no maximum or minimum points. Okay? Okay, so before graphing, we have one more task to do. So again, I'll give you the recap. So we look for the main, we look for the intercepts, we look for the asymptotes, we look for the intervals in which the function is increasing or decreasing, and then we look for the maximum or the minimum, and then the last step. So you have 1, 2, 3, 4, 5. The last step before graphing is for you to identify what are the intervals in which the graph is concave up or concave down, and we have to identify the inflection points. Okay, concavity depends on the second derivative. If increasing, decreasing, and maximum or minimum highly depend on the first derivative, concavity and inflection points will depend on the second derivative. Okay, so the function is x over x minus 1. So first derivative, so we found the first derivative to be negative 1 over x minus 1 squared. So we have to find the second derivative through the use of the first derivative. Now, one faster way of getting the derivative of this, aside from the quotient rule, is by writing this as negative x minus 1 to the negative 2 and use the chain rule. So the second derivative would be, so this will be negative 1 times negative 2, that's 2. Then you have x minus 1. So minus 1 here should be negative 2 minus 1 is negative 3. And then the derivative of x minus 1 is times 1. So this is equivalent to 2 over x minus 1 raised to 3. Okay, so same idea. If we have critical number for the first derivative, we have the possible points of inflection for the second derivative. So first, it's a possible point of inflection because we have to test whether it is really a point of inflection. Okay, so same idea. The possible point of inflection will happen either when the second derivative is 0 or when the second derivative does not exist. And again, in this fraction, there is no way that this will become 0 because this is already 2, and the only way that this expression will become 0 is that when the numerator is 0. So we go to the second option. We look for the value of x that will make this undefined. And that is simply when x is equal to 1. Because if this is 1, then the denominator will become 0 and the second derivative will become undefined. So to analyze the second derivative, it's the same idea with the first derivative. So get a number before 1 and get a number after 1. So if I will choose 0, so 2, and if this is 0, so this is 2 over negative 1. Negative 1 cubed is negative, so we expect this to be negative. If we pick a number at the right of 1, say 2, the denominator will become positive, and since 2 is positive, then positive over positive will be positive. Okay, a negative second derivative means it's concave down, so just name it as CD, and a positive second derivative is concave up. So to answer the question, where is the function, or what is the interval in which the function is concave down? So concave down from negative infinity to 1, and then concave up from 1 to positive infinity. To answer the point of inflection, the point of inflection is where you change concavity from concave up to concave down. And the only candidate for that is x equals 1. And if we check it, it's concave down and concave up. There is a change in the concavity at x equals 1. Therefore, the point of inflection, so this is POI, this is POI, possible points of inflection. But the actual point of inflection will be when x is equal to 1. Then we just have to identify what is the corresponding value if x is equal to 1. But unfortunately, 1 is not part of the domain. Okay, so there's no y for x equals 1. So we're not lucky to have a point of inflection actually. There is a change, however, it is undefined at x equals 1. So even if it's a candidate for the point of inflection, we still cannot consider x equals 1. Just to add to that, a point of inflection should be part of the domain. So it just so happened that the value, the possible point of inflection, is not part of the domain. So we were not able to get a point of inflection. Okay? So the third video, so there will be a third video. In the third video, we'll be combining everything that we found from the first step to the last step to graph the function. But for now, we will end with the 6 steps. These are actually the preparation in graphing the function. Okay, that's it.